Hello, can folks hear me? Okay. Hi, everyone. Welcome to the Forum on Physics and Society's award session. Very happy to have you all here with us today. We're going to deviate a little bit from the agenda in the beginning to recognize two of our new fellows that were sponsored by the Forum on Physics and Society. So could I please have Dr. Kathy Turner to the front up here on the stage? Okay, thank you. Dr. Kathy Turner is the Cosmic Frontier Program Manager in the Department of Energy's Office of Science in the Office of High Energy Physics. Cosmic Frontier researchers use naturally occurring data to reveal the fundamental nature of matter and energy in the universe, including the nature of dark energy, dark matter, and inflation. Turner plans and oversees the world-leading program, including interagency and international coordination and partnerships. Since starting at DOE in 2000, she has shepherded the program of many small experiments to its current portfolio of projects and experiments at larger scales, providing even more precise scientific results. She has served as the DOE representative or chair of many committees for projects and program reviews and federal advisory groups, including the Astronomy and Astrophysics Advisory Committee with the National Academy of Sciences. Turner received her PhD in high energy physics from Florida State University in 1989, based on research at DOE's Fermi National Accelerator Lab. As a postdoc, she worked on the D0 experiment at the Fermi Tevatron for University of Maryland and New York University, where she carried out measurements of the W boson mass. She was a staff scientist at DOE's Brookhaven Lab before taking the position at DOE. Her citation reads, "For leadership as a program manager at the Department of Energy, enabling significant advances in the areas of cosmology, astronomy, and astrophysics." And I'm pleased to present you with your pin and your certificate. Okay, should we take our photo? Okay, are we good?
Okay.
All right, and I would pin it on you, but there you go.
Okay, thank you.
Thank you so much.
Thank you.
Thank you.
Appreciate it.
Congratulations.
Thank
You're welcome. Okay, I am pleased to invite Dr. Kartik Sheth to the front. Oh, they know you're at a conference, so. Okay, Dr. Sheth is the Associate Chief Scientist for NASA, and he will deliver the third talk in this session, and I will read his full bio then. But the dissertation of his APS fellowship reads, "For outstanding, innovative, and sustained leadership of inclusion, diversity, and equity efforts in astronomy and astrophysics and the nation." And congratulations, here is your certificate.
Thank you very much.
And your pin. So now you can deliver your talk with your pin on.
All right. I will do that.
Thank you. Okay. Great. Well, can we have a round of applause for our new fellows? All right. Thank you. So next, I am pleased to introduce Dr. Galileo Violini, the 2024 Joseph A. Burton Awardee. The Burton Award recognizes outstanding contributions to the public understanding and resolution of issues involving the interface of physics and society. His citation reads, "For establishing programs in physics education and research in Latin America and the Caribbean that increased regional scientific capacity, for promoting international scientific cooperation across continents and regions of the world, and for creating the Centro Internacional de Física in Colombia." Now I'm going to read a bit more about Dr. Violini. Dr. Violini is an elementary particle theoretical physics and former professor of mathematical methods of physics at the Universities of Rome and Calabria. He is co-founder and director, now emeritus, of the International Physics Center of Bogota. He received the John Wheatley Award of the American Physical Society and Abdus Salam Spirit Award of the International Center for Theoretical Physics, Abdus Salam. Dr. Violini is an honorary member of the Colombian Academy of Exact, Physical, and Natural Sciences. He's a fellow of the World Academy of Art and Sciences and a fellow of the American Physical Society. Dr. Violini was a former UNESCO representative to the Islamic Republic of Iran and director of the Tehran office. His other roles include Doctor Honoris Causa of the Ricardo Palma University of Lima, consultant to the governments of Guatemala and the Dominican Republic, and to UNESCO, CSUCA, ICTP, and other international and national and international organizations. He is co-chair of the Executive Committee of the Great Caribbean Light Source Initiative, LAMISTAD. He is author of some 400 publications on science policy, theoretical physics, and science education. Will you join me in welcoming Dr. Violini to the stage? Can you give it a test?
Yeah, now to move the transparencies.
Yep, I recommend using the arrow buttons, and what we do is we're going to click start for you, and that will get your slides up. Should. Okay. Let's see.
I charged it this morning, it worked.
Okay, so we will see, and this is a pointer if you...
No, I'm not going to point.
Okay.
No, but it's...
So our slides should be working. Okay, it takes a minute, all right.
Okay.
All right.
And now to move, just...
And then I would just click the arrow.
okay. Okay.
I think it's the side arrow. Yeah, all right. And you
Okay.
have 30 minutes for your talk. And
Yes, I think I will be able. Thank you, Anna. For my presence in this session is as a recipient of the Burton Award. For me, it is more than a conventional pleasant duty to express my deep gratitude to the American Physical Society and to the Forum on Physics and Society for this prestigious recognition. It is a great honor to join the impressive 50 years long list of previous awardees. 30 years ago, I was receiving the J04 Award. I promised that it would stimulate me to pursue further the ideal of my model, Abdul Salam, to promote science in the developing world in a holistic vision encompassing science, education, and peace. Today, the acknowledgement that I kept the award with APS and the Forum on International Physics makes me excited. This has offered me this opportunity to present some reflection about the lesson one can draw from what might have led to select my name among so many colleagues who are everyday testimonials of the role that science and physics play to make the world more equitable and the society more equitable. Indeed, there's been some success with a common bottom line, a long-term vision. Often, external conditions may suggest that a goal has little, if any, chance of being achieved. However, the seeds can bear fruits for future harvest. The pessimism of the reason should never prevent the optimism of the will to be the compass of our activity. And this is especially true in the context of developing countries. Developing countries share the burden of historical delays in science and higher education policies, often accompanied by social and economic inequalities that demand vigorous and difficult decisions. 50 years ago, to talk about high-energy physics in the Andean region could have seemed crazy. It was a delicate and difficult task to advocate with Marcello Cini, a giant I had the fortune to collaborate with, the right of young Colombian scientists to follow their vocation in the country, without being forced to migrate or to make the research in few areas supposedly relevant in the national context. A few years later, at CIF, the International Center of Physics that I founded with a dear Colombian friend and colleague, Eduardo Posada, and with the support of a dozen of colleagues, the top of that seed was a small group of young physicists. Some of them would become university rectors, dean of faculties, head of departments, or lead important scientific programs. And there was a second fruit. CIF promoted, with the collaboration of Leon Lederman and José Antonio Rubio, a broad regional commitment in fundamental physics. And this commitment paved the way for Andean groups to go to Fermilab and CERN, also thanks to another program, the Broad LM program, which was promoted by Luciano Maiani, Veronica Riquer, and again by Rubio. And now, decades later, Ecuadorians, Colombians, Peruvians are regular active participants in the LHC experiments. When I had first advocated for African-Latin American collaboration at the end of last century, it would have seemed to be a nonsense dream. Nevertheless, few weeks ago, it was exciting to hear that the Brazilian president, Luiz Inácio Lula da Silva, has been speaking at the African Union Summit, and this is a confirmation that now interregional scientific collaboration is in the world agenda. In fact, as a matter of fact, it was not considered a strange curiosity by the Dominican government when last year I decided to include in a two-day symposium program to consider also looking at the Gulf and Maghreb countries. Actually, such kind of collaboration is being put in place with a beautiful example of the synergy between the African light source and the great Caribbean light source. I had the fortune of being involved in a program of reconstruction of the University of El Salvador after the Civil War, and of being the director, UNESCO director of Tehran office in Tehran, and UNESCO representative to Islamic Republic of Iran. In El Salvador, I could, with another friend, James Very, convene a meeting to design a science development plan for Central America. Among the participants, there was a young Guatemalan, Fernando Quevedo. The direct, unpredictable drop of that seed was 20 years later, because Quevedo became director of ICTP, and it launched a needed and ambitious program of regional doctorates in Central America with me and with another colleague. Now, who knows how that experience in El Salvador was instrumental to make him such extraordinary and visionary director of ICTP. And in Iran, when I met Reza Mansouri, and we could contribute to make possible the long-expected participation of Iranian scientists to CERN. Well, there's a point. These experiences were not part of my duties. And this allows me to dare to suggest to who may have in the future similar responsibilities, don't be bureaucrats. Always interpret your duties extensively. Be confident that supervisors will understand. Never look at why something may appear to be impossible. Try to find how it can be made possible. However, if I look back to those achievements, I cannot say that I'm satisfied. Yes, I feel myself honored, but I'm happy to be here. But this is a subjective pride, and this is not enough. The needs of the countries and the region where I've been working for about 45 years would have required much more. And the sad story of this, the sad side of the story is that 45 years later, most of these needs are still the same. It looks like if the out-of-time Macondo atmosphere of Garcia Marquez's 100 Years of Solitude pervades science policy. It is a scandal, not an amazing curiosity, that the talk I gave for the J04 Award ceremony is still actual. And it is more than anecdotic that a few months ago, I could write an article for a Dominican Republic online newspaper. That article was a plagiarism of something I'd said and written with Marta Lucia Guardiola and José Luis Villaveses 35 years earlier at the TWAS conference. Too many problems are structural. Too many Latin American countries have an economic matrix based on volatile items, tourism, services, remittances. High-tech is imported, not produced nationally. Even less is object of advanced research, despite the popularity of a magic word, innovation. This reflects and is rooted on their scientific and education system. Science is Cinderella. It is mentioned in electoral campaigns, but rapidly forgotten the day after the election when the attention shifts to everyday urgent problems. The average Latin American investment in science is now, as decades ago, of the order of 0.6% of the GNP, but differences between countries are huge. The mantra goal of the mythical 2% is transmitted from a generation of policymakers to another, and there are differences within the countries, social, geographical, sometimes ethnic, those between capital and small towns and villages. This makes the fundamental human right to access and use science, approved unanimously by UNESCO in 2017, remain one of those wishful decisions of United Nations applauded in the summit speeches but not reflected in actions. Science and education are entangled, not only in UNESCO acronym. They require harmonious policies. However, their national plans don't used to be entangled. Little is done to assess their implementation. The illusion of innovation and technological development without facing structural problems is cultivated. Nobel Prize would say, warning against the pitfall of research of immediate application and supposedly, I would add, useful to the society, is not part of common politician education. Short-time actions are often politically more rewarding than creating infrastructure, be it a center of science, be it an important facility. New Melibey, quoted by a famous Latin poet, many politicians are terrified of the idea that a barbarian opposite political party may enjoy the benefits of their policy. Sometimes the return of investment is harvested decades later. Brazil entered high energy physics 40 years ago. And I remember Thiomno at Fermilab proposing to two brilliant, probably this is too early. To two brilliant theorists, Carlos Escobar and Alberto Santoro, to make the brave decision of moving to experimental physics. Now, a few days ago, Brazil has just joined CERN as first American non-member state. Among the expected benefits, let me just mention one. Yearly, against a duty of $11 million, it will have access to a portfolio of tenders of $500 million. Perhaps this may explain, at least in part, why certain proposals did not succeed, despite their goal should have been recognized as a must for a country or a region. Therefore, I prefer to talk about what could not materialize. And this is not because, as an Italian poet of the 19th century, Guido Rozzano, wrote, "I love only the roses I did not pick, that could have been and were not been. But because understanding why those roses could not be picked, lessons are learned, and hopefully this will help me, or whoever may be in the future, to pick those that still deserve to be picked. The successful creation of CIF in Colombia was due to several fortunate time and space coincidences. A visionary president, Belisario Betancourt, excellent science administrator in Colciencias, the Colombian Research Council, Efraín Otero and Fernando Chaparro, a scientific community that supported the project without looking at pet individual or institutional interests. There was a generous regional vision that led to establish offices in Peru and Ecuador, anticipating what ICTP would have made decades later when it created 4 satellite centers in Mexico, Brazil, Rwanda, and China. Research centers are useful. The best assessment of ICTP impact is provided by the South Scientific Development during its 60 years of existence and the centers established having it as a model. Unfortunately, there's also some failures. In Spain, Gregorio Medrano is the person exactly in the middle, if you look between the king and Salam, is Gregorio Medrano, promoted an intercultural center that in some way recalled the idea of Toledo of the 14th century. It never took off. After local elections, the new majority did not understand the strength of the idea. No, this potential was understood when Medrano received a few years ago the Spirit of Abdus Salam Award, rare, perhaps unique case of recognized and unrealized idea. In the US, the extraordinary experience of Iowa Institute of Theoretical and Applied Physics, ITAP, promoted by James Very, lived the space of a morning, only a few years, because of cuts in the state support. Among its important lines of activity, there was not only science, it was pioneer in gender capacity building. In Peru, Multiciencias, promoted by Víctor Latorre, could not resist the strain of the economic change introduced by Fujimori government. I was witness of those cases as a spectator and advisor of these visionary friends. In other case, again sadly too many, I was instead the promoter. It has been impossible to convince the Andean countries that a Trieste Light Center for the region is necessary to complement those in Mexico and Brazil. Twice I was close to success. In Colombia, a few days before starting to realize the project, first there was a change of rector in the university where it was expected to arise. Then the following rectors showed an alternating interest that did not allow to rescue the project. It remains a mystery how the political importance of such a center in one of the most vigorously developing regions in the country, the Latin coast, did not receive more than a generic attention by local politicians. Few years later, the same project was considered and supported by Ecuadorian government. The feasibility study was not implemented because the realization was delegated to a university whose rector suddenly changed his mind and stopped the project despite the diffuse interest existing inside the institution. Also in this case, the social and economic impact in one of the less developed provinces of the country transcended the scientific value of the project, and the project should have deserved a more vigorous political support. These centers belong to what UNESCO calls C2C, Category 2 centers. There are some 20 worldwide. In Latin America, only the 2 I mentioned. Something similar happened in Dominican Republic. There was a project for a regional center of material science. The support was granted by 2 important private universities. It fitted with one of the most developed areas of national research. All this was not sufficient. Personal interest, worse, jealousies, different priorities of the government, consequence of a higher education system in which much of the advanced research is made in private university, which limits their capacity, A mixture of these clauses? I don't know. But certainly a basic problem is that limited 0.6% of the average GNP investment in science, a percentage that in most Central American countries is much above the reality. 9 years ago, during the meeting of the regional Central American doctorates, I launched the proposal to create a regional fund for science and technology. It would have remained an academic provocation had not been for the lucky circumstance that the government of Guatemala and its vice president, Juan Alfonso Fuentes Soria, endorsed it. More or less it was approved. 9 years after, it has not yet been brought to the attention of the Central American Head of State Summit. What is missing? Diagnostic may provide different answers. First of all, society support. Of the whole civil society, not only of the scientists. Often scientists are biased by the wrong idea that science funding is rigid and that new projects mean less money for theirs. Structures open to the society, such a regional association for advancement of science, may be much more effective than scientific society, that in some cases, and I had an unpleasant first-hand experience for that, but I don't mention it, may be dominated by small groups of mutual admiration and interest. Moreover, not necessarily good scientists have the vision of promoting other sectors. I had the fortune. I studied in Rome. After the Second World War, Edoardo Amaldi could have made physics at the University of Rome be focused only on high-energy physics. He did not. However, promoting the diversification is not always successful. An emblematic case of lost opportunity in Latin America is that of gravitational waves. They were the subject of the first workshop we organized at CIF 40 years ago. The key opening speaker was Amaldi. Audience was from all the region. There was no follow-up. Latin American presence in the discovery has been minimal, even if very important. Actually, Gabriela Gonzalez is one of the main representative of that group. No, a better fate had a second attempt when the Italian spokesperson of the experiment, Fulvio Ricci, participated a few years ago in a Dominican Republic symposium. Differentiation is the only way by which developing countries' science agenda may be autonomous, and the collaboration with advanced countries will not be as if they were Pygmalion Professor Higgins or Colonel Pickering. However, to make them behave as new Eliza Doolittle is not trivial. It is not easy to convince policymakers that by differentiating the lines of scientific development, opportunities open for that industrial and high-tech development that only can make their country be in the next decades more than a tourist destination, a market and a service provider. And the same holds for the authorities of the universities, especially if private, who rarely understand that the first beneficiary of cultivating some new niche will be their own institution. Science scope is more than scientific or economic development. It includes a better society and peaceful international relations. Responsible scientists must assume a holistic civil commitment, not limited to their specialty. Often, they will be ignored or have little chance of impact. It is a fact. It is necessary to have scientific journalists, possibly with access to TV popular channels. Unfortunately for this, I don't have marvelous results to present as evidence. But I'm proud of the little support I could give advocating on non-scientific press the equitable availability of vaccines and the liberalization of the patents during the COVID pandemic. Now, to conclude, I will mention two more experiences based on education and science, but of a much broader scope. They could have been important. They still are. Thus, let me make a call for the tremendous challenge of their rescuing. My first contact with Haiti was the catastrophic 2010 earthquake. In the following years, with ICT support, we were very close to achieve the goal of launching an integrated national plans of education and science. The crisis of the last few years has stopped this initiative. I'm not so naive to be not aware of the many IT problems, but among the conditions for any solution, a vigorous education program is a must. And moving to another region on which worldwide attention is concentrated, the Middle East, after October 7, the hostages tragedy, the civilian death in Gaza, the destruction of scientific education and health infrastructure, it is difficult and embarrassing for me to imagine what science can do. Nevertheless, let me end with a word of hope. Some 30 years ago, I met two magnificent scientists, Riyad Safafta from Palestine and Aviv Yavid from Israel. They had made a visionary proposal, a center of science in the region of Eilat Aqaba. Eilat is in Israel, Aqaba in Jordan, where scientists of the region could work together. I was an enthusiastic supporter of their proposal. Two milestones were my participation in a UNESCO conference in Jerusalem and the mission for UNESCO together with two American colleagues, again James Very and Hildegard Very. This and the experience of ICTP being instrumental for the development of the tertiary sector in Trieste even led me to suggest that Gaza could instead be the ideal location for such a center. Today this may seem out of question. Obviously it is unthinkable. However, also the 100 years war at an end. My experience at UNESCO, the lesson of a great Director General of that organization, Federico Mayor Saragossa, made me a convinced ambassador of the preamble to UNESCO statutes. The defense of the peace must be built in the minds of men and women. Our hope must be and are the young generation. I have a dream that I can see at least that I can see at least the launching of a minor initiative, such as that suggested by another Iowa colleague, Szilard, a kind of periodical conference where young scientists from the Middle East may meet, know each other, perhaps work or at least create the condition for future work jointly. An experience of this kind has already been possible and successful in the same region. Sesame Synchrotron shows that through science, historical barriers can be overcome. The main raison d'etre of this recognition I am receiving today, so intimately related to societal development, is to motivate young people who, pursuing the same goals, may be successful where the previous generations I should say in my case, was not. As a Latin American by adoption, I want therefore to conclude dedicating this talk to young Latin American scientists, and that many others join me and the 1992 awardees, those who were honored for laying the groundwork for the agreement between Argentina and Brazil to abstain from building any explosive nuclear device. Thank you for your attention, and I cannot conclude without expressing once again my deepest gratitude to all the colleagues, of whom only few I mentioned, without whom I would not have been here. Thank you.
I have a question for you. So I forgot to introduce myself. So I'm Dr. Anna Quiter. I am the chair of the Forum on Physics and Society. I should have said that in the beginning. And so my question for you, I really appreciate this note of hope that you ended on with dedicating your talk to all young Latin American scientists. And I'm wondering, Can you say a bit about how you maintain that hope in the face of all of these challenges? You also talked about Gaza. We know that we've had sessions on nuclear
Yes.
war and et cetera.
Well, I can tell you, first of all, let me tell you one thing. I will give a talk next week in a big laboratory where I was recommended not to talk about that. Anyway, here, since APS is a private organization, I can tell. I think that, frankly speaking, the problem there is a tremendous problem. And the history of that problem has roots which go very far away, so that if one looks at the past, there is no solution. However, when there is no solution, one must find a solution. And the point is that I understand all the difficulties that there will be, because, of course, one thing I used to say is the following, that if one takes the arguments favorable to the Palestinian part, and the arguments favorable to Jewish-Israeli part, and the arguments against to each of them, each part could write a book like that, a cahier de doléances and a book of arguments in favor, which have a basis. Of course, one should try to forget it. And I give you an example. I was mentioning my experience in El Salvador. El Salvador had a tremendous civil war in the end of the 80s, beginning of the 90s. However, when the matter was to make the discussion for peace, and the same happened in Guatemala, people who had killed the father or the mother of the other person on the table were sitting at the same table. It is not the same in Middle East. This I also realize, because the unity existing in a country is more than the problem existing in the Middle East, where there are additional of a religious element. Each religion has also extremists. I mean, but these are complex realities. And so I don't make the mistake of considering all the people in Palestine Hamas. I don't make the mistake of considering all the people in Israel, those who think that it is legitimate to kill any Arab because he's an Arab. I mean, I hope that the reasonable people prevail. And I hope that they can seize it.
Thank you. Any further questions? We have time for one more.
No.
Okay. All right. Well, thank you. Please join me in thanking Dr. Violini. That's okay.
That was great.
Okay. So I am pleased to introduce Dr. Bob Budnitz, the 2024 Szilard Lectureship Awardee. The Szilard Lectureship Award recognizes outstanding accomplishments by physicists in promoting the use of physics for the benefit of society in such areas as the environment, arms control, and science policy. His citation reads, "For outstanding leadership in formulating and guiding the U.S. Nuclear Regulatory Research Program in areas of reactor safety, waste management, and fuel cycle safety, and for significantly advancing seismic probabilistic risk assessments as applied to nuclear power worldwide." Now I'll give you a more complete introduction to Dr. Budnitz. Dr. Budnitz has mainly been involved with nuclear reactor safety and radioactive waste safety, with one emphasis being on seismic safety. A member of the National Academy of Engineering, the APS, and the American Nuclear Society, he remains active after having retired in 2017 from the University of California's Lawrence Berkeley National Laboratory. Prior to 2002, he had a consulting practice in Berkeley, California for over 20 years. In 1978 to 1980, he was at the U.S. Nuclear Regulatory Commission as Deputy Director and then Director of the NRC Office of Nuclear Regulatory Research. He was also the technical coordinator of the NRC's special inquiry into the 1979 Three Mile Island accident. In the 1980s to 1990s, he chaired both the NRC's expert panel on seismic margins and the National Research Council's Committee on Remediation of Buried and Tank Wastes. For many years, he was heavily involved in assisting Eastern European countries to upgrade their reactors' safety. He holds a Bachelor of Arts from Yale in 1961 and a PhD from Harvard in 1968. Please join me in welcoming Dr. Budnitz to the podium. Try it again. Give that a try. I turned it on.
Okay, does that work? Good.
And I will get you started. And the timer is right here.
Okay, thank you. My name is Bob Budnitz. I came here from Berkeley, and it's a real honor and a pleasure. And the reason it is, in an important way, is that when I think about the important people in the generation ahead of me in physics who influenced national and international policy, Leo Szilard is in the group of 4 or 5 most important people in that time period. I haven't got time to go into that now about why, but everybody here ought to go read about Leo Szilard because of his tremendous and important influence during World War II and then afterwards with arms control and leading the way and showing why that's so important. I'll just leave you with that and go on. My talk here is nuclear engineering. I have a PhD in physics from Harvard, but I'm a nuclear engineer. It turns out, as I look back, that the physics training, experimental physics, was the best training I could imagine for nuclear engineering. It taught me a whole lot about engineering, which is design and things like that. And it also taught me a whole lot, just a whole lot about how to do something that's practical. So I'm going to talk today about a field that I've been working in for the longest time. It has to do with the seismic design of these large nuclear power plants that are around the world. And I'm going to explain why we have confidence, you can see the title, that the design of nuclear power plants against earthquakes is adequate. Now, you're going to have to decide yourself whether it's adequate. I'll come to that later on. But I'm going to explain why the community has confidence that it's adequate. Now, what do? Page down? Oh, you hit that. I see it. Okay. It's not page down. It's a little arrow. So my objective is to explain why we have the confidence that I mentioned. And I'm going to talk about what it means to say that a seismic design is adequate, explain how the design process works, and then later explain how the overall complex system can be designed to work as a whole. Because you can design components, but they have to work as a whole. I'm sure you understand that. So that's the objectives of this, and I'll go through them. There really isn't enough time to dwell on all the details in detail, but I'll go through them. Now, it's important for you to understand that when you're designing something like a seismic anything, that the owner has to make some crucial decisions before the design can proceed. I'll just give you the example. Think about this building. This building was designed for seismic, right? You hope. But the question is, what is the design criterion? What is the end point of the design? It turns out that in the California Building Code, the end point of a design of a building like this is to assure life safety for the occupants. Life safety for the occupants. The building code does not require that this building function afterwards. The owner may decide that, and I believe that the owner of this hotel did decide it's supposed to function afterwards, but it's not in the code. And it certainly isn't designed to be totally elastic so that after the design earthquake, I'll talk about in a minute, that there's no discernible damage, okay? So that's important. Now, let me go on. The other crucial thing is that although a building like this has to actually, by code with margin for the design earthquake, which I'm going to come to next, function for life safety of the occupants, the building code requires hospitals to function afterwards. We understand that, right? Not regular buildings, but fire stations, hospitals, they have to function afterwards, after the earthquake you're talking about. But nuclear power plants have an even stronger design, and I'll come to that in a minute. The second question is, how big an earthquake? Small earthquakes come along frequently, big ones come along rarely, really big ones come along very rarely. How often is too often for the earthquake that the design is supposed to meet? Is it once every 100 years? Is it about once, if it's a stationary Poisson process, it'll be, every 100 years means 10 to the minus 2 per year. Of course, it might not be. Is it once per 1,000 a year, or is it lower still? So let me describe. For a nuclear power plant, the design endpoint is that every safety relevant item, structure and equipment, must be totally elastic for the earthquake that it's designed for. Totally elastic means when afterwards you got to go and look at it and there's no change. It hasn't changed. It's as if the earthquake hadn't occurred. That's the design endpoint. That's not the design endpoint for hospitals, by the way, but it's the design endpoint for nuclear power plants. Crucially, for nuclear power plants, the design earthquake for which that is so is chosen to be around 10 to the minus 4 per year, or even slightly lower. And I'll show you how that's come about in the next slide or two. So that for nuclear power plants, the earthquake is going to be a very big one because it's very rare. And after it, everything has to be totally elastic by design. And I'm going to come to the next part because that's the hard part. Now, you have to decide what the seismic hazard is for your site, and it's going to be dependent on the site. This site, for example, is different than a site 50 miles away, and you understand that perfectly well. And of course, it's site dependent. But the way the seismic hazard is determined for the purposes of a design is you have to identify all of the nearby seismic sources. If there's a fault, sometimes back east, there isn't a discernible fault, so it's understood that there's seismicity in an area which has to then be accounted for. But after you've decided where the nearby seismic sources are that are going to affect the building that you're in, you have to analyze how the seismic energy propagates from that source to the site. Because if it's east or north, even if it's at the same distance, it may propagate differently. You have to analyze that. How do we do that? Well, all over the world there are these little tiny earthquakes, magnitude zeros, and you can measure that. So we can understand how it goes from source to site, but there's uncertainty. It relies on data. There are analytical models and the like. And then once the energy from the postulated source comes to the site, and it might be a source that comes around every 1,000 years or every 10,000, and it's very different, then you have to do an analysis of the effects of the site itself. Is it a rock site or a soil site or something in between? Because motion that comes into a rock site doesn't get attenuated very much, and motion on a soil site does get attenuated and in fact gets frequency shifted compared to the incoming motion. And there are inhomogeneities at the site that have to be accounted for. And all of this analysis is done for every nuclear power plant site, site-specific. And then once the energy gets to the base mat of a big structure like this building, it has to propagate up into the structure. If you're on the 8th floor, it's going to be different than if you're on the ground. And for a nuclear power plant, which can be, meters and meters and meters high, it can be quite a difference. And not only does it have to propagate in terms of getting attenuated or even sometimes amplified, but it gets frequency shifted. 5 hertz motion can come in and end up at 2 hertz or 10 hertz by the time it gets to the place where the heat exchanger is that you're worried about. So all of these things are done specifically for every site and for every nuclear power plant. There's a protocol for doing all of them. There's methodology. It's all been worked out for the longest time, lots of practitioners. and it's reviewed, and this analysis is done so as to understand what the seismic environment is for some particular item that you're analyzing. Maybe it's a heat exchanger, or maybe it's the building, or maybe it's the whole thing. And that analysis, which I haven't got time to go into, I could give you a whole lecture about it, but there isn't time, then produces what we call the seismic hazard environment. Now I'm going to go to the next slide and show you a typical seismic hazard curve. This is a typical seismic hazard curve in California. And the dark line is the mean, which is very close to the 50th percentile. But these are major uncertainties. I'm going to try to explain. The abscissa is a load. That's spectral acceleration. This happens to be at 5 hertz. In G's, you know what a G is. G is the acceleration for gravity. And I want to go up the 1G line right in the middle. And you'll notice that, that the mean earthquake that's going to produce 1G comes around about 5 times 10 to the minus 4. Can you see it? It's between 1 to the minus 4 and 5 times 10 to the minus 4. But if you go up and down to the 5th and 95th percentile of our confidence, because we have uncertainty, the uncertainty is plus a factor of 3 or 4 or minus a factor of 3 or 4. We don't, in other words, the best knowledge in a place like California where we really understand a lot has uncertainties like that. Now let's go the other way. Let's pick the 10 to the minus 4 earthquake. Well, the black line, the mean, is around 2G. But the 5th and 95th go from around 1G to around 3G. You can see that. It's about a factor of 2 in the size, that's the shaking. And the probability has this other thing. So it's very uncertain. Given that it's uncertain, the Nuclear Regulatory Commission's regulations insist on a lot of extra margin so as to make sure that even if our knowledge is, this is our state of knowledge, even if our knowledge is at the 95th or the 5th, we're still okay. And that extra margin is built into the codes. Now this is a typical plant in the West, and I want you to go look at the 1G line. The 1G line goes from about 10 minus 4 to 10 minus 3. See it? Now this is a site in the east. And 1G is way out here at the left. These are gals, and there's sort of 1,000 of them is 1G. 1G is way out at the right-hand end of that. And you can see that the median is around 10 to the minus 7, and it goes from 10 to the minus 5.5 down to something much lower. Okay? In the east, 1G earthquakes they just don't come around. We don't worry about them. But in the east, the heart of the curve that you worry about is about 1/3 of a G. At about 1/3 of a G, you can see about 300, on the abscissa. You go up there, and it goes from 10 to the minus 4 to around 3 times 10 to the minus 3, looking vertically. So in the east, there's even more uncertainty, even though the numbers are smaller, because we don't have big earthquakes in the east for experience, as opposed to California, where it's, quote, narrower, even though on a log scale it's big. So there's a lot of uncertainty in these numbers of what we call the seismic hazard, and that's the input. And the NRC's regulations, and all around the world, insist that you use the conservative end to make that input to do the analysis and the design. Now here's another way of explaining it. On the abscissa here is the frequency in hertz of the motion. Way down to the left is about 1 hertz. In the middle is 10 hertz, and at the upper end is 100 hertz. Fast vibration. And the bulk of the energy goes between 3 or 4 and 5 and 10 hertz. You can see that's where the energy is. One curve is the 10 to the minus 3 curve, the 10 to the minus 4, that's 10 minus 3 per year, 10 minus 4 curve, and 10 minus 5 curve. So if you're designing, you have to take this into account. The 10 to the minus 4 per year earthquake has a certain frequency spectrum, and it depends on whether the heat exchanger is sensitive to 3 hertz or 10, or the building might be sensitive to 2 seconds, which is a half a hertz. Okay? All of that has to be taken and is taken into account in this design analysis. Oops, got to go the other way. Now, I'm going to talk about the behavior of an individual item. Let's just imagine it's a piece of electrical equipment. Maybe it's a heat exchanger, it's a valve, it's a cabinet, it's a pump. For many items, understanding how that behaves in an earthquake is only understood by doing tests, or sometimes looking at real earthquake experience data. We have these huge shaker tables the size of this room. I'm going to show you a picture of one in a minute. You put the item on a shaker table and you shake it until you see where it fails to perform its function. Either the rotary pump gets out of line, or the shear wall starts to fail, or whatever it happens to be, or the piping leaks, or whatever it happens to be. So for many of these items, we understand how they behave with tests, and in some cases with real experience data, going out and looking for earthquakes, okay? Now here's a big shaker table just as an example. This is in Japan. If you didn't know these things exist, I'm showing you. This is a 4-story building erected on a shaker table in Japan, and you can actually shake it up to earthquakes bigger than they've ever experienced and see where it fails and how it fails and under what frequency and how sometimes it's the duration and so on. These large shaker tables are the basis for our understanding at what point these things fail, and therefore you got to strengthen them until they don't, so that when we have confidence that it isn't going to fail, it's because of these tests. Now, there's also real experience, earthquake experience. Here's an example. Everybody's probably is driven by a refinery, and you see these great big tanks. Well, here's one. There might be 50 tanks. You can see the damage, and you can, with seismometers, a real earthquake, you can see at what level this fails and what level that fails. And then, by the way, you can reproduce it at a shaker table. And we use this real experience data in places like Turkey and in Chile and in Alaska and in Japan as a means of backing up our understanding of things that you really can't analyze. You've got to do it by test and experience. On the other hand, go to the bottom here. Some things we understand using analysis, like structures, big tanks, piping. We benchmark them with a test, but we actually do analysis too. I'll just leave you with that. Now, in the end, this is an individual item. Every item in a nuclear plant is designed using the appropriate design code, as, by the way, it's every building. This building is designed to an ASCE civil engineering code for seismic. But the electrical in this building is designed to an IEEE code. And the concrete is designed to American Concrete Institute code. And the same thing with nuclear, except the codes are made nuclear with a lot stronger, with overarching design coordination from the American Nuclear Society. So each individual item is designed to a code that has been put together by the best experts and benchmarked and the like. I'll just explain how that goes for an individual item. Now the outcome is something that we call a fragility curve. Now a fragility curve on the ordinate on the abscissa is the load, some acceleration, okay? And on the ordinate is probability of failure. Now if we really knew things terrifically, you notice what happens here. The thing doesn't fail at 0.4 G, and it fails every time at 0.6. See it? See how steep it is? It's almost like well, that's an unrealistic, we don't know anything that well. A typical fragility curve more looks like this. See that one? It looks like this. A typical fragility curve might start to fail. Remember, we do these tests. A small fraction of them fail at 0.2 G, half of them fail at 0.5, and they've all failed by 0.8. It's a lot of uncertainty, which you have to take into account. If you really want high confidence, you better design that thing so it's strong at whatever load you decided was the 10 to the minus 4 earthquake that you're worried about, which I told you about before. Okay? And we do this analysis, we benchmark it against the tests, and then we go on. Now let me talk about a typical nuclear power plant item. This isn't the plant, this is an item. Typical design input loading, I said, you would go to that curve, it's around 10 to the minus 4 per year. But the design codes have margin and conservatism. The target of the design code is typically around 10 to the minus 5 per year for an item. The idea being there's high confidence it will withstand a load about twice times the design input load that you chose because the codes have this extra conservatism and still perform the function. Now there's a lot of uncertainty. I said at the bottom, the uncertainty comes because there's a variability. A 1G earthquake may be 30 seconds or it may be 10 seconds or it may be 90 seconds. A 1G earthquake may have a whole lot of 5 hertz and not much 1 hertz or a whole lot of 10 hertz and not much and so on. So there's a lot of variability. There's a variability from one item to the next. So you put 10 pumps on a shaker table, they're not all going to fail at the same motion, just variability. Because of that, that leads to that uncertainty that I told you about, right here, okay? Now, the outcome is for an item, you can work out what the probability of getting in trouble is. You do a convolution of the hazard, that's the thing on the left, that's the input motion, and the fragility. So you go to 0.2 G and there's a few percent chance of failure, and go to 0.4 G and there's a 20%, and you go to 0.6 G and there's a 50%, and so on. You do the convolution, and when you're done, you can work out for that particular item what the probability is per year. It might be 10⁻⁴ in the end, that item is going to get in trouble by a convolution of the hazard and the fragility, and that's for an item. Now I'm going to turn to the plant as a whole. To understand the plant as a whole, you have to understand individual accident sequences. An accident sequence begins with the earthquake initiating event, but then there are some other failures. Maybe the earthquake, you have the earthquake of a certain size, it damages the DC bus, it damages offsite power, it damages a rotary pump, it damages something or other, and sometimes one of the other failures is a human error. The human fails to do something right. And in the end, you can add the different failures A and B and C contingent on the initiating event, and you can work out for the facility as a whole, identifying individual accident sequences. In a typical analysis like this, there are a few dozen of them, and in a typical analysis, I'll come later, there are a much smaller number that really matter. But you can do this for the analysis that I said here for the convolution for individuals, but then you gotta do it for the group as a whole. And by the way, sometimes the A plus B plus C is a Boolean and. They both have to fail. Sometimes it's a Boolean or. If either fails, okay? Well, if either fails, it's the weaker one that gets you in trouble. If they both have to fail, it's a stronger one. And you have to understand that before you go through this complex analysis. So here I go. Back in the 1970s, when this analysis was being pioneered, it was actually thought to be impossible. A typical, I mean that in the most strongest way. When the first analysts were doing this, many engineers said, this is impossible. You can't identify all the accident sequences. You can't get enough information to be able to do this convolution. You can't understand the hazard very well. We will never understand the fragilities, and those accident sequences are just very, very difficult. Too complicated, too difficult to quantify. But decades later, we've had a huge amount of experience and benchmarked some of these analyses with real earthquakes, not at nuclear power plants, but you can do it for a refinery. You know, there are refineries have seen big earthquakes, even not many nuclear power plants have. Well, the only one ever that really mattered was at Fukushima. But in any event, because we have a lot of experience, it's not only not impossible, it's done routinely. It's not only done routinely, there's an international standard for how you do this analysis. You do this, you do this, you do this, you do this, you get peer reviewed. There are 100 requirements, or maybe 75, I'm not quite sure. And the committee that put that together, I actually chaired the committee that put it together and was the chair of that for about a decade. I'm no longer because I'm retired. And we have benchmarked this against a whole lot of experience and believe that this analysis methodology is robust. And that's how we do this analysis. It's called probabilistic risk analysis. Now here's a typical result for the facility as a whole. This is a typical nuclear power plant. It turns out we analyze 50 or 100 sequences depending on, and at any given plant, only 5 or 10 of them are important. The others turn out not to be. Important means that they're getting in trouble at a frequency that I show you here, typically around 10⁻⁵ per year. The other ones are smaller still. 10⁻⁵ per year is a pretty low number, but we're designing this, remember, for an earthquake that comes around about 10⁻⁴ per year, okay? And then there's this extra margin. It turns out that the total accident frequency at a typical plant like this, adding up the 5 or 10, is several times 10⁻⁵ per year. This is seismic. But most of those sequences don't produce a large release. In fact, as you know, 3 Mile Island didn't produce a large release, okay? The large release frequency is several times 10⁻⁶ per year. That's where we come out. Now the uncertainty on that is plus or minus a factor of 3 or 5, or maybe even 7, maybe even 10. There's a lot of uncertainty in it, and we are unabashed about that. But nevertheless, that's a typical result for a large plant like this, and it is peer-reviewed, and we have lots of experience, and we believe it within those uncertainty bounds. Now, here's what I said. Why do we have confidence? There's lots of experience analyzing and testing individual items. We have over 100 nuclear plants that have done the entire analysis. There are hundreds of practitioners at the international meeting. We'll have 200 or 300 people at the international meeting, never minding the ones that didn't come. And we have a lot of actual earthquake experience that validates pieces of this model, not for the whole nuclear plant, we don't have a lot of those thankfully, but some. And that earthquake experience data has validated within the ranges of uncertainty the sort of analysis that we've been doing, and that's why we have confidence. Now, how likely is a major core damaging nuclear power plant accident? I just told you. We've had over 100 analyses, I said that before, it's widely used. There's a wide circle of international peer review. Anybody does one of these things, they have peer review, and there'll be foreigners and Americans and lots. And I already said the last two things here. The typical mean core damage frequency for a plant like this from earthquakes is several 10⁻⁵ per year. A large release is lower because only a small fraction of them produce a large release. The rest of them damage the plant, and it's no good anymore, like 3 Mile Island, but it doesn't produce a large release. Now, summary, why do we have confidence that we understand these questions? Lots of experience, lots of benchmarking, and a hell of a lot of data, okay? Not on plants themselves, but individual items. You do have to put it together. However, whether that's safe enough and adequate is not for me to tell you, it's for you to tell yourself. Whether, I'll read it to you, whether nuclear power plant accident frequencies in the range that I've told you about is adequate is an individual decision. Individuals can decide. That's not adequate for me. I don't want to live near that thing. That's not adequate for me. I'm going to petition that it shouldn't run. The Nuclear Regulatory Commission has made this decision affirmatively for core damage frequency in this range. And they regulate to it, and there's margin, okay? Whether that's adequate for you, it's for you to decide. So when I said, why do we have confidence that we understand these questions, whether it's adequate has two halves. You understand this, but I'm going to try to go through it. One half is whether you believe the analysis within the uncertainties, and if you don't, then you have even less confidence. But even if you believe it, even if you think, gee, that analysis is about right, you yourself may decide that 10⁻⁵ per year isn't adequate for you. Okay, we're all grown up here, just so you do it honestly. It's an individual decision, and in around the world, it becomes the decision of the regulatory agency. I don't have to explain that, but I will. In the US, we have the US Nuclear Regulatory Commission. There's an agency like that in every country that has reactors. There's one in Brazil, and there's one in South Africa, and there's one in Russia. And there's one in Armenia, and there's one in China. All of them regulate to ranges in this, for seismic, in this range. That is, the regulations for seismic around the world are very similar, okay? And the reason they're similar is because the community that put together the whole structure is international in its composition. I'm one of them, I'm proud to be one of them. And there are, 2 or 3 dozen of us, and we all know each other, and something new comes up and we'll communicate. And so this community is either, depending on whether you're optimistic or pessimistic, a check on individual cultural bias, or, as the pessimist might think, groupthink. I can't tell you whether it's groupthink or not because I'm one of them. But we don't think it is. But on the other hand, if you go do this analysis and do a whole lot of peer review, and everybody comes in with more or less the same, with some disagreements about details, then this is where we end up. Okay? I'll just leave you with one more thought. There are 2 major pieces of uncertainty that continue to bug my community. The first is that humans are involved in these accident sequences. You have a big earthquake, this fails, this fails. Some humans got to go and secure this thing. Some humans got to inject this thing over here. Some humans got to, okay, you understand. We try as hard as we can in the community to understand the probability they're going to do it right, because it's not 100%. After a big earthquake, it might only be, they might make an error one time in 10 just because they're concerned, or gee, we had this big earthquake and my wife and kids are, or my husband and kids are over here and I'm worried about them, never mind the plant. We have experience about that from refineries and even from nuclear power plants like at Fukushima, and we understand those error rates, but that continues to be a plague on our uncertainty. The overall uncertainty that we've come up with in these analyses embeds that as best we can, okay? And the second is the issue about correlations. If I have 4 pumps and I put them on a shaker table, I showed you that curve with the large uncertainty. One of them is going to fail at 0.3 G, and one of them is going to fail at 0.4 G, and one of them is going to fail at 0.5 G. All right? But for certain items, although there's a variability, there's a lot more correlation. They're really all going to fail similarly. We've struggled to, the community, here I am, we've struggled to understand those correlations. We've struggled to make sure that we capture those variabilities and the uncertainties as best we can in terms of trying to embed it in the uncertainty. But it remains a kind of a nagging plague to us, and it's easy to explain why. Because for a lot of things where on the shaker table we haven't seen a lot of correlation, you always say to yourself, but at a nuclear power plant, they might have something that would lead to a correlation, which would make it much more probable than we have estimated. That's something we worry about. The whole community thinks we've got it right because we put a lot of uncertainty plus or minus on that. But the two things that plague us are the human error question, have a big earthquake, humans got to do some things, and the correlations question. So now let me come just briefly, it'll only take a few seconds. The advanced reactors that are now being discussed have in many cases taken most of the human actions out of the accident sequences after an earthquake. They've designed them so the human doesn't have to do almost anything. Great. They've also taken great care to design away correlations. If you have 2 pumps, let's order one from GE and one from Siemens, right? You'd be surprised how that diversity, rather than merely redundancy, can make a difference to your worrying about correlation. So although that wasn't the case for the plants we're running now, some, but not all, a lot of that thinking has been there from the start in these advanced designs so that we can design out from the start some of the things that trouble us to make sure that we really don't have the problem that I just mentioned of being overly optimistic. I'll just leave you with that. The talk started out by saying why we have confidence that the design of nuclear power plants against earthquakes is adequate. Well, we have confidence that it is what I told you. You get to decide whether 10 to the minus 5 per year is adequate. Okay? Just one last thing. I started life as a physicist. I got a PhD in physics, experimental physics. But I realized going through that I really didn't want to be a physicist. I wanted to be an engineer, okay? And I'm not decrying that. Everybody makes their own decision. It turns out that in retrospect, the physics training was the best training I could have imagined compared to having gone to graduate school in engineering. I'm not putting down engineering, God bless them. It just, for me, it was the right thing. May not be right for you, either physics to engineering or engineering to physics, you know. I'm sure you understand that, but I just wanted to explain that as a piece of the personal history. And the last thing is I want to just say one sentence about Leo Szilard. You should go read about him. When the war was over and the bombs were dropped in Japan, Szilard immediately began to organize the physics community to try to influence policy that we shouldn't start building 100 of them, never minding, you can finish this sentence for me, never minding build bigger ones. And he carried on that campaign as its leader, or one of its 2 or 3 leaders, until the day he died. He is, for those of us that really think arms control and non-proliferation, all that stuff is important, he is one of our heroes going all the way back to before the war. And that gives me a particular pleasure to be honored with the Leo Szilard Award. Thank you very much. And I came in, I was a minute over.
Okay, thank you so much. We have time for a couple of questions. If you'd please come to the microphone for questions, because it's recorded. Yep, so the microphone in the middle there, if you don't mind.
That was okay.
Yeah, that's great.
Well, thank you for your presentation, but I would make a comment more than a question. I'm afraid that whatever one says, whatever one says about the feasibility without risk, the real problem for the society is the existence of the so-called principle of precaution. Unfortunately, there are people who are convinced that even if the risk is 1 over 10 to 20, it is not acceptable. The case of COVID is very clear. So what I would say is that you convince me, but don't forget that in the society there are a majority, not majority, but a substantial fraction of the majority who would never be convinced of any fraction of security, safety you provide.
Well, I want to not only agree with you, but I'm going to try to make a point which is related but different. The community I'm in has struggled to get our arms around what the real number is for the risk to present to society, including its uncertainties. That's what we're doing. You get to decide, or you broadly. I think I said that. Yeah.
That was a great talk. So I have a question. I spend a lot of time teaching young engineers and young physicists, and I talk to them about the frontier. So for these kinds of problems, what do you think the frontier is now? The edge that we need to discover? Where do we go next is it how we talk about risk? Is it how we evaluate risk? Is it mechanical, doing better calculations? Where's the frontier?
The frontier in the field I'm in is to identify the places where the risk arises, or we have uncertainty about it, and design them out. What I mean by design them out, you can't design out, we can't retrofit to the existing reactors a whole lot of different things.
Sure.
A best way of saying it is, if I have an old plant that was designed in the 1970s, I can make it great, but I can't turn it into a modern plant, right? Because of some features that you just can't. But the new ones can design it out. And in fact, in the field I've been working in, the new designs look like they have cleverly designed out many of the most important contributions to these sequences, or they've enabled us to reduce the uncertainty and then work on the rest of it. So that's a frontier in engineering. The frontier is looking back on what's there, looking at its design, its flaws, and so on, and fixing them one by one. Now, just to give you the example that's completely obvious to me, I drive across the Bay Bridge from Oakland to San Francisco all the time, okay? The eastern end is a new bridge. We only built it 20 years ago. It is way better than the old bridge built in the 30s. Not because they were smarter, but because we got 60 years of experience. And the frontiers in engineering are generally taking advantage of that, plus advances in science, to integrate to a design that's better.
Sure, thank you.
Well, thank you very much. Please join me in thanking our speaker. Okay, and a reminder for folks that Dr. Violini and Dr. Budnitz will be recognized tonight at the APS Award ceremony, so please feel free to join that as well. Thank you very much. Thank you. And then our final speaker today is Dr. Kartik Sheth. Those of you who were here in the beginning saw him receive his APS Fellow pin and certificate. And so I'll read his bio. Dr. Kartik Sheth is a world-renowned observational astrophysicist whose scientific research has primarily been in the areas of galaxy formation and evolution, star formation, and the interstellar medium. His somewhat non-traditional career path has taken him across government, academia, nonprofits, and influential roles within the White House. Dr. Sheth is currently the Associate Chief Scientist for NASA. Previously, he served in the White House as the Program Examiner for the Department of Energy's Office of Science at the Office of Management and Budget, and before that, as the Assistant Director for Research Infrastructures and Science Equity at the Office of Science and Technology Policy. In addition to a stellar career in astrophysics, Dr. Sheth's work has spanned a vast range of science and technology topics, from artificial intelligence and machine learning to clean energy technologies, climate resilience and sustainability, advanced manufacturing, as well as establishing extensive international scientific partnerships in Chile, Brazil, and South Africa. Dr. Sheth earned a BA in physics from Grinnell College in Iowa, a MSc in physics with a thesis in physics education at the University of Minnesota, and then a MSc and PhD in astronomy and astrophysics at the University of Maryland in College Park. He was a postdoctoral fellow and then a permanent staff member at Caltech and was tenured at the National Radio Astronomy Observatory. He has over 180 refereed papers with over 25,000 citations. Throughout his career, Dr. Sheth has championed inclusion and equity, earning him the NASA 2021 Medal for Diversity, Equity, and Inclusion, and as you heard in his citation, was one of the features for his election as an APS Fellow this year. Please join me in welcoming Dr. Sheth.
Thank you. I know it's late, so hopefully I'll try to do some audience participation, so please do participate. I'm really glad to see some of the students and postdocs who I have met here at this meeting come because I have some examples of changes that I have advocated for that you might consider using in your career. So those pictures were from Mumbai through the cornfields of Iowa to NASA, and my talk is entitled Reflections on Advancing Science Through Inclusion. But where I really want to start is where I was born, and I think in your talk, I think it was very clear to me how important it is where we come from, because that influences a lot of who we are and how we approach science. I grew up in Mumbai on the West Coast. My family, those mountains are the only time I saw snow before I came to America. Back in 1980, the only time we were in Kashmir. And my childhood was, just very different than the way I live today. We grew up in a relatively poor family, did not have constant water, much less drinking water, never had a television, car, or refrigerator. And one of my fondest memories was renting a bike for an hour, and you got to come ride it in your building's compound, and that was fun. And one of my memories, because an uncle of mine came to America in the 70s, is they would say, "Oh, we have drinking water at any time," and I would just imagine them being able to hold out their cup, and the glass would automatically fill with clean water, right? But that wasn't my childhood. What really got me excited about science were school field trips to the Nehru Planetarium, a Voyager picture book that my uncle and aunt gave me, and I knew everything about the planets when I was a kid. And then the two TV shows that came to India first were Different Strokes and Star Trek. And every Sunday I would go running around the building trying to find out if somebody would let me watch Star Trek on Sunday morning. And so that's what got me excited about wanting to be an astronaut. I got glasses at 10 and decided I'll be an astronomer. Wasn't a bad choice. But this is my school. And the lessons I learned really, discipline, service, friendship, gratitude, and respect for teachers really have served me well. And I'm showing you this to make a point, so just bear with me here. This was my school, started by the two people you see on the left, Sir Thomas and Madam Phillips. Christian school, even though I'm not Christian, very, very secular school. And these principles that they taught us have served us so well that 25 years later, we all assembled again in Mumbai. And what impressed me was how every single person in my class had followed those childhood principles. Everybody was involved in some kind of public service. Everybody loved exploring the world. And I was just amazed by that. And I was wondering, why did we all do so well, even though it was a pretty modest school and most people were from fairly modest backgrounds? And I think the most important principle is that in those times, I knew I belonged. I belonged in my home country, I belonged where I was, and I didn't feel alien at all. And I performed my best. And that's the lesson I want you to take away, is please try to create situations in which you make everybody you're working with feel that they belong and are included in the work that they're doing. we came to America when I was 14. Typical tumultuous immigration story. We came to America for a better life as a family. I didn't start the timer. I should start that. Oops, sorry. Okay, you'll give me a 5-minute warning. Yeah. Okay, so that would be good. How much? 25 left?
21 till your 5-minute warning.
Okay, good. So the family came to America to have a better life as a family, but we were immediately split apart because we didn't have any money. So my dad moved to New York, my sister had to move back to India. I ended up going to 3 different high schools in 4 years. And when I ended up going to Grinnell College without ever having visited it in the middle of the farm country, it was a spot of stability. And it taught me some really important lessons, and I'm just leaving those up there for the students. But I loved Grinnell because I felt like I really belonged, even though it was in the middle of cornfields. And then I ended up going to graduate school, where for the first time, I encountered an incredibly toxic and racist environment. Now, all through this time period, I was always an excellent student. I was either first or second or third in my class. And I never thought the environment could impact me, until I ended up in such an environment where I stopped going to classes, where the environment truly impacted my ability to be the student that I had always been. I came back to Grinnell that Thanksgiving break, and my professor said, so you want to quit physics? Are you quitting because you don't like physics, or because you don't think you can do it? And I said, no, I love physics, but I don't think I'm trained to do it. I wasn't good enough. And they said, don't worry about it, go back. We know we've trained you well, but you should not quit physics because you don't think you can do it. I went back, the students got together, in fact, my class, and we filed an EEOC complaint against the Department of Physics. And there was a whole investigation, but nothing but a slap on the wrist for the department. But that experience of almost really giving up on the dreams, my parents came in their 40s and emigrated from India for me and my sister to this country, and almost leaving science altogether, really emblazoned on me this desire to never have to go through that again and make sure that other people don't have to go through that again. So that's the start of my journey of trying to advance science through inclusion. So what did we do? We didn't just sit around after the investigation. We just started making some grassroots changes. I started a Women in Physics series. Dr. Faizenberg Silov was one of our first physicists. She told us the story of how she'd been rejected thrice from going to grad school, even though she had better grades than her husband, because her husband was considered to be the breadwinner. But she said she never gave up. And she said the 3 things you have to remember to be successful in science are to be single-minded, focused, and thick-skinned. And the latter one is one of the most important for people of color. We started Dinkytown dinners, where we would take 2 different faculty members just to dinner with graduate students to just open up lines of communication. There was a climate committee that was formed, and the astronomers really came to my rescue. One of the things that really helped me, and which I try to teach students and mentees now, is to develop a free agent mentality. It's a baseball term, but it's the idea that you have to develop confidence in yourself that you will be okay, that you don't need to be part of a toxic, racist environment, such as that you should be able to walk away from it and trust the fact that you will be okay. And that's very hard, I know, for a lot of people to believe, and they tend to stay in environments that just grind them out. And I always encourage people to leave. So we made some grassroots changes. I came to Maryland and immediately was asked to go to a sexual harassment prevention workshop. And at the end of that workshop, they said, who wants to be a trainer? So I raised my hand. And since then, I've done hundreds of workshops as a trained sexual harassment prevention trainer. And I will say that was something that was an initiative of the president at the time. And she believed that every single person on the campus should have an environment where they should feel safe and feel empowered to be able to study whatever they wanted to. And these workshops, which really were just simple training workshops, they were not punitive, had enormously important impact. So there are starting to see how we make systemic changes. So I'd encourage you to get involved in such things that your university or community might offer. I went to Caltech after getting my PhD at Maryland. And just very quickly, just give you some examples of kind of things we've done. There's an article in Nature called ethical gray zone that you might want to take a look at that Caitlin Casey and I wrote. And that stemmed from a workshop we did at an Aspen school, where we realized that there was a lot of bad behavior in our community and a lot of people were being poorly impacted. So I took the lessons from the sexual harassment prevention workshop and converted them into these ethics workshops that we have then done and other people have emulated around the world. And that was a very positive thing for our community. For science collaboration, which is called the Spitzer Survey of Stellar Structure in Galaxies, which is the deepest infrared survey of nearby galaxies, we ended up writing a policy where we said that nobody should be able to say, well, this is my science, and nobody else can write a paper on this. And we believe that all data should be made available to the community in science-ready form within 6 to 9 months after we take it. And that open access policy, this is back in the 2000s, really is now being adopted elsewhere, but many parts of our field have adopted that policy. And it's a way to say to people, you know, we're not trying to carve out any science. We want to welcome people to work with each other. On the Committee of Status of Minorities and Women, I started doing, you know, the committee met, but what we tried to do at the American Astronomical Society meetings was to always have evening happy hours or dinners out to try to build the community. So again, very simple things, but as you can see, what we're trying to do are making cultural changes here within the environment that you work in. And then when I got to the National Radio Astronomy Observatory, I founded the National Astronomy Consortium, which still is in existence. It's a partnership with 17 historically black colleges and universities, 7 predominantly white institutions, and three centers, using something called the Posse Foundation model. And these cohort models have been incredibly transformational. To give you an example, when we first started that program in 2011, there were only 2 African-American women who were tenure or tenure track in astrophysics in all of the United States. I know that number sounds really surprising. It surprised me at the time. There were only 8 men and 2 black women. In the 3 years after we started this program, we had 6 African-American women based on this cohort model that we built. This summer, the last one will get her PhD, and all 6 of them have gotten their PhD, so I'm really, really happy about that. 2 of them also got the Hubble Fellowships, and both of them are going to be faculty members at UMass and University of Chicago. So I say that to really inspire you to say, you know, even small programs can make a big difference, but you have to do it in the correct way. And I'll come back to that in a second. We used a similar model in a program that we established in South Africa, and that has had an impact across Africa. I'm going to Morocco in a week and a half to now expand that program using NASA data. The nice thing about that program is we are really able to create the first astronomer, for example, on the continent, Mark Harris in the Ivory Coast, or the first radio astronomer in Kenya, Naftali Kimani, et cetera. Some of the other things that I really enjoyed doing were also changing the hiring practices as the first director for the Office of Diversity and Inclusion for our lab. To give you an example of a hiring practice you can think of, and again, I'm going to use a little sports metaphor, so I apologize for those of you who don't know baseball. But in baseball, the leadoff hitter is very important because we want them to make it to the base. And in the Washington Nationals, there used to be a player named Trey Turner who looked perfect. You know, he would hit the ball perfectly, had perfect form, would run to the first base very quickly. And then there was a player named Juan Soto who came, I think, from the Dominican Republic, who just didn't have good form. His feet would be inside. He'd be standing in a weird way. It was also fast. And the question is, if you're the general manager for that team, if you're the hiring manager, who would you hire? Now, most people say, oh, I want to hire Trey Turner because he looks perfect on paper. But a good manager always hires Juan Soto because they're looking at the fact that this person has such potential for improvement, that they're already good. So as you're thinking about hiring graduate students, postdocs, or colleagues, maybe you want to think about what else they bring to the team and whether the things that you think they're missing are things that they can develop. That way you multiplex your advantage. And we wrote those policies into a program called APS and our proposal for the recompetition, and have been using that since then. You guys may have heard of the Team Up report. Our committee, LCERM, for the American Institute of Physics, put that together, and Arlene Knowles is now running that. These are the students from the NAC and the 9 program. On the very left is Buntu Chabetsa. He's just finishing his PhD in South Africa. RL's person, and she just finished her degree in atmospheric science. All of the others are astronomers or astronomer PhDs. So anyway, then I want to talk a little bit about the systemic changes that we've made after coming to NASA. So after spending 6 years at the National Radio Astronomy Observatory in Charlottesville, where probably something bad happened to me or Aaron Evans, the black professor who I did the NAC and the 9 programs with, I just needed to take a break. So I was like, I'm going to take it easy at NASA and not work so hard on systemic, cultural, other changes. So we did simple things. We just created a code of conduct, which surprisingly didn't exist, for how panel reviewers should treat each other. And in addition to doing the code of conduct, which had a lot of resistance, especially from old timers who were like, why do we need this? This is BS. Everybody knows how to act. And I was like, all right, well, if you know everybody needs to act, then you have nothing to worry about. But we ended up polling reviewers over 2 years to ask them how important this code of conduct was. And 70 to 80% of the respondents were very, very positive, but especially younger people who felt that having that code of conduct allowed them to feel included in panels and contribute. So that has been very helpful. We've changed how we assemble panels in NASA astrophysics in some of our programs. For example, I always start by asking people of color to be on my review panels first, because I know from experience that they are being asked 10 to 1 compared to most white reviewers. And as a result, I'm more likely to have a difficult time recruiting them. So what I try to do with my panels, if I want them to be diverse, is I go to the groups that are going to be the hardest to recruit, get them onto my panel first before I go to other panels. And our panels are really some of the most diverse panels in astrophysics. We've focused a lot on examining the language we use. Words like calling a spade, or words like ghetto, because those words inadvertently are part of our lexicon, but can have a really a large impact on people who feel hurt by them. And that might, again, seem very small, but we started a Speak Up series, and it's been very powerful. I was just at the OMB, and we also have started that there. And then lately, I've also been focusing a lot on Asian Americans. Asian Americans are 6% of the American population. And they are 13.5% of the professional workforce, but they're less than 2% of the corporate leaders. Even in tech firms, where there might be 30% of Asian Americans in corporate tech firms, they are not well represented. Because Asian Americans are viewed with the model minority myth, and usually viewed as very good at being good workers, but not as leaders in America, even though there are leaders elsewhere. So we've been working a lot on that. Here's the code of conduct that I mentioned to you before that we've adopted. So then in 2020, how much time do I have?
You have 13 minutes.
Okay, great. So after the murders of George Floyd, Ahmaud Arbery, and Breonna Taylor, I felt like I was sitting on the sidelines, and some young people came to me and they said, we can't just sit tight. So how many of you have heard of shutdown STEM, hashtag shutdown STEM, okay? Right, so that's what we did. I was part of the 9 people who did shutdown STEM. And I had no idea how much impact a social media campaign can do. But we did manage to shut down STEM around the world for a day, and really started a lot of conversations about how to change the science community when it comes to increasing inclusion. In the previous administration, in the Trump administration, Jim Bridenstine, who was our administrator at NASA, you will be surprised to hear, perhaps, that we adopted the core value of inclusion at NASA. So inclusion is one of our 5 core values. And one of the great things about adopting that as our core value is that it has allowed us to do many, many programs. As you can see here in the bolded work, at NASA, we believe that to achieve greatest mission success, we want to embrace hiring and developing and growing a diverse and inclusive force in a positive and safe work environment where individuals can be authentic. And in addition to that, we went a little they're in Science Mission Directorate, which is where a lot of the science is funded. And we wanted to make sure that we created an environment of inclusion. But I felt like this wasn't enough. We really needed to do actions. And when our associate administrator, Thomas Zurbuchen, asked me to co-chair what he called the Diversity, Equity, Inclusion Group, I said, I really don't want to do that. The time right now is for us to make real change when it comes to people of color. So he and I co-chaired the ARAG, which is the Anti-Racism Action Group. And this was our statement: address the lack of equity and inclusion of the Black, Indigenous, and people of color community in and within SMD, which stands for Science Mission Directorate stakeholders. Now, we wanted to go beyond just words. We wanted to talk about actions. So we committed ourselves to saying, this group, which was only 8 of us, we are going to disband in 3 months. But our challenge was to come up with actionable ideas that we would implement, because words are cheap and actions are hard. In order to do that, we decided to adopt a design thinking process. How many of you have heard of design thinking? Just a couple of you. So I encourage you. There's a nice book called Design for Change by Jean Litka. I took a class in the Darden Business School called Designing for Individual and Organizational Change, which is where I learned about it. And this is a great technique, which I think as scientists and as physicists, we already intuitively know, but we don't know how to practice when it comes to human beings and people. What design thinking does is slows down the process when human beings are involved. And the first step here, what is the problem, is something you and I and all of us as scientists are really well trained to do. But then what happens in design thinking is the second step, which again, I think intuitively you all know, which is to come up with the boundary conditions for the solution for the problem that you're examining. So here, for example, what we call attributes of a solution, before we even started brainstorming for actionable ideas for ARAG, we decided that these are some of the key things we should think about for what a solution should hold. So solutions cannot repeat doing the same things that we've been doing for the past 3 to 5 decades and expect different results. For example, we shouldn't be focusing on building pipelines, because we've been doing that forever and numbers just haven't changed. We need to really question the underlying assumptions. For example, a lot of people think that the reason minority-serving institutions are not participating in our nation's ecosystem is because they don't have good sponsored research offices, or because they have too high a teaching load. But that is us, those of us who went through R1 institutions like Maryland and Caltech, thinking this is how it worked for me, and this is what they don't have, and that's why there's a problem. And we have to stop that kind of thinking, because it's not our thinking to do. We really need to go and figure out what is the reason why people are not participating. So we came up with this attributes of a solution, and then after that, we did design thinking incubator workshops to really try to get all ideas on the table. We generated over 200 ideas, out of which we selected 8 of them, and we implemented them immediately. Now, it was really, really important for us to have the associate administrator for the directorate as a co-chair with me, because, of course, with any kind of work like this, you're going to encounter resistance. So it was really important for me to be able to pick up the phone, call him, and say, hey, Thomas, this is where we're running into a problem. How can we solve this? And having that leadership buy-in was incredibly critical for us to do this work. The first one is also another really useful tool. We tied the bonuses of people with senior executive services to how well implementing IDEA. Now, I didn't talk about this. I said, I'm not using DEIA on purpose, even though that is the federal language. We put IDEA as the words that we're going to use, because in fact, inclusion is much harder than diversity. I can tell how diverse this room is. I can count the number of people who appear to be female, number of people of color. But how do I know if the room's inclusive? And because that is harder, that is what we need to pay attention to. If you can create an inclusive environment and then add diversity to it, you're golden. But if you try to have diversity without inclusion, you will make divisions worse, okay? So inclusion is much, much harder, but I encourage you to really think about that, and I'm happy to chat more about this afterwards. How are we doing, right? So we did this work for 3 months. We generated 200 ideas. We have over 60 people involved in a IDEA working group now. Some things are doing really well. There were people who were looking for an outlet to plug into this way of changing the way we change our culture and the way we do things. This has been great for them in our directorate. We've been doing the regular monthly conversations now, and people are learning about various aspects of how to be more inclusive. We've done a climate study and really looked at whether people feel safe or not. And in at least 2 divisions, we have sustained activities, including some interesting new programs. However, 97% of the leadership in the Science Mission Directorate is white. We actually have decreased diversity. We have coordination for the IDEA working group that's been outsourced to our contractors. And there's, in my opinion, a lack of sustained support that we saw right after the murders of George Floyd, Arbery, and Taylor. And that's not atypical. I'm not saying that as a criticism. I just think that whenever we are doing this work of increasing inclusion, diversity, equity, you're going to take 2 steps forward, and then you will take a step back. And you have to persevere through that activity. You just have to keep going and not be dejected by that. We also see climate surveys are showing disparate outcomes for people of color versus people who are not people of color. And so that's something we need to address. So we think that that has been a good thing, but it's also showing us that changes in the external environment and just general fatigue is taking their toll. In the divisions where things are continuing, in the astrophysics division, for example, we have now implemented inclusion plans. And they're required for many of the solicitations, but it's not the plan that is really creating culture change. It is really the fact that when we ask our community to do a plan, they go, oh my God, you're asking me to do something I'm not an expert at it. And we're like, we know you're not an expert, none of us are, but just try it. And then what we do is we take their plan and we go through and we try to have a discussion about them in ways in which they could improve that. And that is really helping our community tremendously. I presented this to DOE. Kathy wasn't there, but all directors were there, and they've adopted peer plans for all their solicitations. And now these criteria are now a part of evaluation criteria for several of our mission proposals. So you're going to see some more novel and innovative ideas come out of NASA, so keep an eye out for that. Last couple of years, I've been at the White House in multiple different capacities. So now I'm going to talk about some national and international changes via policy and budget measurements. First of all, when we published the National Strategic Overview for Research and Development Infrastructures, in the Science and Society team, we added the importance of human infrastructure and the importance that science cannot be done without its people, so we need to consider them. And now we are really trying to implement a way of thinking amongst the US government that says we need to go beyond. We really need to think about leadership from the factory floor to the C-suite. We're creating structured plays for implementing IDEA, and I'll show you an example of that, starting with international partnerships in the Global South. And somebody was mentioning to me today, Anna was, that she found the congressional justifications for DOE Science. I was the examiner for DOE Science for the 25 budget, so you can take a look at those. Here, for example, is the language and the recommendations for the Space Manufacturing Technology Report that we just released, the Vice President just released. It says, recommendation 5, focus on increasing the diversity in leadership positions across the space sector. Representation matters, and when historically excluded groups see people like themselves in positions of leadership, they're more likely to join the sector's workforce. And thus, it is critical for us to focus on both ends of the workforce pipeline, from the factory floor to the C-suite, which I think most people don't. They just say, oh, let's focus on the pipeline. And I think that's a mistake. Here, for example, is the kind of plays we are creating. This is a document we're working on right now at the White House. And what we are hoping to give people is a set of plays with a checklist and questions to be able to try to see if they can increase IDEA within their research and development infrastructures. So I encourage you to look for this document when it comes out. We're going to get some agencies to prototype this and pioneer this. This is an interagency effort where RDI managers can look at a checklist. If they get stuck with the checklist, they can go to the questions, and we include resources so they can see other examples across the US government and private sector where people have tried to answer some of these questions, so they can take lessons from that. This is I had the pleasure of working and writing the budget chapter for DOE at OMB. Here, for example, is the language in the congressional justification. This is, DOE is really stepping into this, and I couldn't be prouder of the work they're doing. It says the Renew initiative, which has $120 million in 25, aims to broaden participation in underserved communities and advance equity and inclusion. And the FAIR initiative enhances research capacity in emerging research institutions, HBCUs, and MSIs. And underserved communities is defined in Executive Order 14011. So it's a well-defined term that we can all talk about. And then finally, as I mentioned at the beginning, we've started to re-engage internationally with NASA, and we are building a new model of partnerships, partnering US faculty members with Africa, and then we'll expand it to South America. Faculty members where we create mentor pods and try to really tackle the next tier of STEM scholars who are interested not in migrating necessarily to the United States, but staying in their own home countries and becoming the STEM leaders. And we want to do that by building strong partnerships with the United States. And then this is my last slide. I know I went through a lot of material very quickly, but I'm happy to talk to people. And more detail. That didn't work. Inclusion is central to the progress of science. Okay? I think if you have a team that's not inclusive, you are not going to get your best results. I think most of you intuitively know that because you all have relatives and families, and I'm sure that you will hear about it from your spouse or your children when they feel they're not being heard. And I know it sounds weird, but we do need to think about this carefully. I talked about why IDEA and not DIA. Three elements that I think you should think about when you think of a solution is your solutions have to be implementable, they have to be measurable, and they have to be sustainable. You can't really kill yourself as being the only person pushing these ideas. Think from the very beginning, how is this going to happen if I'm not around tomorrow? And using design thinking is one way. And because I covered a lot of material, if you can't remember anything else, just remember these two mantras that I think you can build all your idea work on. You can't be what you can't see, and you don't know what you don't know. Okay, thank you. There's a lot of stuff, so I know, I'm sorry, and it's late.
Thank you so much. We have time for some questions, if there are any questions from the audience. I'll start our question timer. And if you do have a question, please come up to the microphone.
It's okay if you don't, or if you're afraid.
Yeah, don't.
Arjun, you're gonna have to keep it short though, because I saw you ask that question in the other session.
Okay, with that notice. I mean, there's been a lot of pushback politically
Absolutely.
about
20 states.
all of this. And you're probably more party to it than I am, because, yeah. So I just wonder about the uncertainties of all this kind of stuff, the stability of it, the sustainability of it. And I personally feel, I don't think the divisions that reflects are going to go away.
Yeah.
They are, in my understanding, very fundamental to what this society is. And it's hard for me to say how they might be resolved. But just in terms of dealing with what you're dealing with, what's your experience, and given what's coming, because these issues are not going away, you've talked about the successes within these institutions, and that's wonderful, and I admire you for what you've done.
It's a great question. It's coming up a lot for us because there are 20 states where there are laws being passed in the United States. As you saw, Texas just laid off, 8 or 15 people yesterday, University of Texas for people in diversity offices. So this is why I'm really trying to emphasize inclusion and not diversity. And when we ask people to write inclusion plans, they always confuse it. And they're like, oh, I'm going to go to MSIs, and I'm going to recruit more diverse people. And I said, we didn't ask you about that. We're trying to ask you on how to be inclusive. We were talking at lunch, and Anna said, well, I'm really glad to see in the DOE science justification, we talked about emerging research institutions and how even in the Republican side of the House and the Senate, that's very well received. Because what we're trying to do is trying to talk about the fact, how do we expand our STEM footprint so all of the nation is involved? And we really have to be able to say economically disadvantaged areas, rural areas, emerging research institutions, all of them have to be at the table in a way that they are going to be in an inclusive environment. So I'm hopeful that if we focus on the worries that you have and I have, won't be as big. Help. There isn't, I think cultural fights are going to continue, but all we can do is, how do I make my team the best? And we have 28 different papers that we read for that RDI framework we're building. And they showed that when you have diverse teams, roughly the percentage increase in your productivity or your excellence goes up by 2 to 3%. It's very tiny. The difference isn't very high. And in fact, there are examples where you just focus on making a diverse team, things actually got worse. And those same set of studies, we found that when inclusion was included, we saw enormous increases in productivity and well-being of a team. So we're using an evidence-based structure to try to argue to people that we really need to focus on inclusion first and creating ways. And I did an incubator workshop at University of Illinois where I have a balloon team with 5 PIs, all guys who are white, middle-aged, came from roughly the same R1 institution culture. And they said, Kartik, why are you picking us to do this workshop? And I said, because you are my target audience. If I can show you what inclusion means, I think we will learn something incredibly well, because they realized that even they were not being inclusive amongst each other. And then they started thinking, oh, if I'm not somebody who looks like me and thinks like me, what must it be like for the rest of my team? And so it's been very, very powerful to do these workshops and focus on inclusion. Did you have a question?
Yeah, it was actually similar to, it's more about how, like you have this sort of White House experience, and I came to the US in 2019, so I saw the end of and the start of the new sort of administration, and I saw the difference of how much this was pushed. Did we have enough time to make it structural? So is DOE already like the peer plans? Is it embedded in DOE?
Well, and I don't think it's, so I've worked in the administration. I would say that even within the administration, like while you see better diversity, I don't think we've actually thought as deeply about inclusion as possible. I was at OSTP when Eric Lander resigned, who was the first OSTP director, because he created an incredibly toxic environment. So just because you have diversity doesn't actually mean that you've accomplished the goal of creating an environment where everybody can thrive. Whereas, as I showed you, inclusion was adopted in the Trump administration by Bridenstine for NASA, right? And that was never challenged. I mean, so I just think we have to think differently about what we are trying to do and not focus solely on diversity. I think you have to focus on inclusion, because I think everybody that we should have an inclusive environment. Then the question becomes, how do we bring in more diversity? And that's where there are people who believe meritocracy is the way, and that there's a magical thing called meritocracy, and people can be, even though there's a lot of studies that say you have 2 resumes that look exactly alike, and they have different amounts of callback rates, et cetera, right? But people still believe somehow that should work. So we've done things like do dual anonymous at NASA for all of our people. We see some biases going away, but then there are other biases that don't go away. So it's just a long struggle. Do one step at a time. Yeah, I don't have a good answer. I just wanted to say to the young people, don't give up, first of all. I mentioned the POSSE model. I encourage you to look it up, POSSE Foundation. That program was founded because a woman in New York City had encouraged a young person from the city who would never go to college to make it to college. And then she saw he dropped out and he was back on the streets. So she said, why'd you drop out? You had so much promise. And he said, I wouldn't have dropped out had I my posse with me. And that's what gave her the idea. So what the Posse Foundation model does, and I encourage you to think about this, is to create cohorts of students and make sure that you get away from mentor-mentee relationships to go to multiple mentors. And you try to think of really going beyond just the basic education to corridor talk and the unspoken rules of what success means. In my entire life, until Anna nominated me for this award and a couple of other, I didn't get awards. I'll put my resume up against anybody. It is as good a resume academically as you will see. But I've just seen now that I'm getting closer to retirement that people of color just don't get nominated for awards. So I thank you. Mm-hmm. It's just a true statement because people are not racist necessarily, although Jorge and I had an interesting conversation about that this morning. It's something called homophily. It's like, you want to associate with people who are like you, who look like you, and that's just sociological. So if you're from the majority group, you have to intentionally think harder to say, oh, who's not at the table? Who am I not including? That level of emotional intelligence is what I want to develop in the next generation of scientists and engineers so we can be better. I don't think it'll change overnight. We just need to be better. If you see a talk and people are showing you pictures of their team members, like NASA does this all the time. NASA would show pictures like, look at our great team. And it's a team that's completely homogeneous. And come join us. And we're like, why would I join you? Because there's nobody on that team who looks like me. So I got my administrator to say, you can still show the picture, but use that picture to say, hey, this is great. I love my team, but we can do better. And so you have to turn whatever you're taking into how you can do even better. Not to be negative about what's happening, but to acknowledge the inequities that might be in there. So I hope that's helpful.
Well, on that inspirational note, please join me in thanking Dr. Sheth.
Yeah.
And
happy to stay around if you want.
Sure, and a reminder to everybody, the Forum on Physics and Society, all of our sessions are recorded and will be made available publicly on the APS YouTube channel. So you can keep an eye out for those in the coming weeks. You can also join the Forum on Physics and Society. It's free. Every APS member can join. And then you will be sent a link in our regular quarterly updates to the community. Okay, thank you very much for your time today.